तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We have been talking about flip-flops, different types of course, D flip-flop, SR flip-flop, JK flip-flop and T flip-flop. We also talked about level triggering and edge triggering. We talked about master-slave flip-flops. So today we will look at the behavior of some of these flip-flops, different types of triggering. For easy understanding of the schematic, the drawing, for easy understanding of the actually the waveforms, I am using a D flip-flop because D flip-flop has only one input. With SR or JK I need to have two inputs. So in order to determine the output we need to consider two inputs at the same time. So since I thought I would explain the difference in behavior, the output of different types of flip-flops in terms of triggering, master slave, positive edge triggered, negative edge triggered, I am using D flip-flop as an example. The same concept can be extended to the other types of flip-flops, JK, RS or T. Now I am assuming a waveform, a clock waveform. This is the waveform of the clock, 0 to 1 keeps going. This is the clock period. Of course in a clock, any clock, any flip-flop clock need not have, first of all there need not be period of the clock from one positive edge to the next positive edge, or from one negative edge to the next negative edge. It need not be uniform. Of course generally regular clock generation, if you do using standard circuits, you will always have uniform periods. In general it does not have to be. Likewise it does not have to be that positive the level 0 and level 1, level 0 and level 1 of the clocks need not be equal. Again if you want to you can make them equal. You might have heard of this term duty cycle. A duty cycle is the time for which the period, the clock is on compared to the total period. The ratio of the on period of the clock, or the high period for which the clock remains high, to the total clock period, that is called duty cycle. Duty cycle can be half if you have positive and negative regions of the clock pulse are equal in interval, equal in time interval, otherwise a non 50% duty cycle. I have assumed an arbitrary clock. My only requirement is it has to go from 0 to 1 back to 0, back to 1, back to 0, back to 1. So an arbitrary clock, and I am assuming that this clock is applied to different types of flip-flop, to a D flip-flop of different triggering with different triggering mechanisms. Edge level triggered, edge triggered, positive edge triggered, negative edge triggered. So first I am applying it to the master slave flip-flop. The master slave flip-flop, first I would like to know the master waveform. Is a master slave flip-flop is a level triggered flip-flop. It is level sensitive. When the clock is high, any change in the input D will change the output. But when the clock is low, of course, changes in the input D will not affect the output. So there are two flip-flops, master and slave. The master flip-flop is a simple level sensitive flip-flop, wherein when the clock is high, changes in D is going to change the output. But since we are feeding it to the slave flip-flop whose clock is low when the master clock is high, the changes that happen will not be immediately reflected in the output of the slave. That is the concept of master slave flip-flop. So what is the change in the master output? So master output is a level sensitive output when the clock is high. So when the clock is low, this is an arbitrary waveform of D. I said it's a good practice. Earlier on I have told you. It's a good practice to change the data or any inputs to the flip-flop only when the clock is low. But I have not adhered to that rule here. I have given an arbitrary D which changes at random. So D remains 0 to start with, becomes 1 somewhere here in the middle of when the clock is low, again goes low when this clock is low. The second time it goes high in the middle of a clock when the clock is high. It remains high for a while, goes low again somewhere when the clock is low. Then again it goes high, and this time it goes low when the clock is high. So you have all types of things changing when the clock is low, both from 0 to 1 and 1 to 0, changing from 0 to 1 when the clock is high, changing from 1 to 0 when the clock is high. I have put all the combinations possible so that we can analyze the behavior of the flip-flop completely. So in a master slave flip-flop, first I am drawing the waveform corresponding to the master output, which is going to be fed to the slave, of course. So master is a level sensitive, level triggered D flip-flop whose output will follow the input when the clock is high. Is that right? So when the clock is low, nothing happens. When the clock here, even though the D changes to 1, nothing happens to the output because the clock is low. At this point the clock becomes high and the D is 1, so output has to become 1. The output remains 1 throughout the period of the clock on. Since it continues to be 1 here, the change from 1 to 0 during the clock negative or clock being 0 will not be immediately recognized, will not immediately reflected the output. This change from 1 to 0 of the D input when the clock is low will be reflected in the output of the flip-flop only when the clock becomes 1 again. Is that right? That is the behavior of any flip-flop. When the clock is low, all the flip-flops behave as if they are in the memory state. So this 0 to 1 transition shows here in the next clock edge, and next time the clock becomes high. But immediately thereafter, when the clock is high, continues to be high, the input changes from 0 to 1, so naturally the output also has to change from 0 to 1. So the D flip-flop output in a level triggered mode is just you have to follow the input along with the clock high. If the clock is low, you just stay put. That is the easiest way to remember how to do that. So this follows this. It continues to be 1. Clock is low, continues to be 1. Clock is high, continues to be 1. This clock, when the clock is low, it goes to 0, but did not reflect the output until the next clock happens, during the next clock period, in the next clock on period. So at this point in time, this 0 to 1 transition will be reflected. So this 0 to 1 transition is reflected here. This 0 to 1 transition is reflected here. and then in between it goes. This 1 to 0 transition reflects here. This 1 to 0 transition will reflect here when the clock becomes high again. And since when the clock is high, the input goes from 1 to 0, output also will become 1 to 0. This is the master output of a master slave D flip flop, or also a output of a level triggered D flip flop. Both are same. Master and slave are both level triggered. So you can call this either a output Q output of a D flip flop when the flip flop works in the level triggered mode, level sensitive D flip flop output, or the master output of a master slave D flip flop. Now in the case of a master slave flip flop, this output of the master is fed to the slave as the input D of the slave, and that will now output will change according to the clock of that slave flip flop, which is the inverse of the original clock. This clock inverted is the slave clock. So now again originally it is 0. Actually I should have written 1 here. I cannot say Q is 0, QM is 0, that doesn't matter. We don't know what the output was. 1 to 0, we started with 1 to 0, again 0 output initially, 0 output initially. This change in the input, which reflects in the change in the output of the master, will go into the slave only when the clock of the slave becomes 0. At this point in time, the clock of the master becomes 0, clock of the slave becomes 1. The clock of the slave becomes 0 here and 1 here. So this is a 0 to 1 transition of the clock for the slave. So this change will come here. Now again, during this period this is on. Once it is high, this change, will this be seen now? Because now this going from 1 to 0 the output. This going from 1 to 0 the output can reflect the slave output only when this point, only when the clock becomes 0. The clock becomes 0, 1 to 0. This change in the master in output can reflect in the slave only at this point in time, but that before that what has happened? Before that master has become 1 again. So this change in the D in between is completely ignored. So at this point in time it was about to go to 0, but then it finds that it cannot go to 0 because the output of the master has already become 1, so it has to follow the master. So the output continues to be 1, and this output becomes 0, 1 to 0, will be reflected at the slave output at the next negative edge, or when the clock goes from 1 to 0. So this gets reflected here. This change is ignored. Is it not? This, not even this change. Ignored by the slave. Likewise, it became 1 here when the clock was low. So when the master became 1, the master clock became 1, the output became 1, and continued to be 1 for a while, and then got 0. But then this one would have been reflected in the slave at this point in time, before which the slave is, before which the master output has become 0, so there is nothing to follow. The slave follows the master output. Master was 1 at the beginning of the clock cycle. Had the 1 continued at the negative edge of the clock, slave would have followed it. But before that, master output has become 0 in between the middle of the clock period. So again, this is also ignored. Now this is interesting in one sense. What we said was, always change inputs when the clock is low. When the clock is high, do not change inputs. Now automatically that is taken care of in this case. Only those inputs changes which were made when the clock was low, change the output of the slave. This change happened when clock was high, that is ignored by the slave. This change occurred when the clock was low, clock was high, ignored. That means as if this input change and this input change, which are both of the value when the slave becomes slave, when the clock is 0, these are the ones which are reflected. So this is the slave output, in which these temporary pulses, these are called glitches. Momentarily the output goes 1 back to 0, from 1 to 0, 0 to 1 back to 0, or 1 to 0 back to 1. These are called glitches, which are undesirable. I don't want glitches, I want a flat waveform, 0, 1, 0, 1, like that. For a set amount of any waveform to be of use should last for a period of less than, at least for 1 clock period. If you want to use it, if you want to use any output, I need to have it at least for a 1 clock period, so that it can activate whatever mechanism or output devices which needs to activate. This is a narrow pulse, very small portion of the fraction of the clock period. This is again a narrow pulse. These 2 narrow pulses are glitches that have been eliminated in the master slave flip-flop. So master slave flip-flop serves the purpose of frequent changes in input affecting the master are not reflected in the output of the slave. It only makes the change once in a clock period. Originally we thought of master slave for avoiding what? Racing. To avoid racing we thought of that, because that is the same as this. In effect this is the same as this, because that was 2 frequent changes within a clock period. Within the clock period being on, there were too many changes in the output which we did not like. So we avoided any changes in the output when the clock was high. That is also the same thing here. So that design, which was originally made to eliminate the changes in the output of the clock, output of the slave flip-flop too frequently, also helps us to ignore glitches. So this is one operation, one option, to have a master-slave operation to make sure that the output do not change frequently, they only change once in a clock period, and any racing condition can be avoided. The other possibility is to use the edge-triggered flip-flop, which is mentioned by me in the last lecture towards the end. I can have a mechanism or an extra hardware within my flip-flop which will make sure that once a clock transition, once a output transition happens, it will not happen again within the same clock period. It will only happen in the next clock period. You can let the output change during the clock changing from 0 to 1, which is called a positive edge transition, or when the clock changes from 1 to 0, which is called negative edge transition. So one is called the positive edge triggered flip-flop, the other is called negative edge triggered flip-flop. In a positive edge triggered flip-flop, all you have to do is to look at the waveform, look at the input at the time when the clock goes from 0 to 1, and whatever will be the output based on that input will be the output for the entire clock period of that clock period. You don't have to worry about what happened in between until the next clock edge comes. The same thing in the case of a negative edge triggered. Once there is a change, you look at the flip flop looks at the input of the clock, looks at the input at the time when the clock transits from 1 to 0, and that will decide the output, and that output will remain same until the next negative edge comes. In between, you don't have to worry about what changes have happened in the output. So the same D waveform, the same clock period, I have now drawn the master's positive edge triggered output. Had this been a positive edge triggered flip flop instead of a master slave flip flop, had it been a positive edge triggered flip flop, how will the output change? All you have to do is to look at the positive edges. This is called the positive edge. This is called positive edges. At the positive edge, what is the output? That output will be the input. That will be the output for the entire clock period. So at this point it is 0. So for the one clock period it is 0. At this point it is 1. For the next clock period it is 1. At this point it is 0. So this pulse is not going to be recognized. This pulse is not going to be recognized. So it has become 0. At this point it is 1. It is 1. At this point it is 0, 0. At this point it is 1, it's 1. Even though it has fallen back to 0, it continues to be 1. So once it becomes 1, it continues to be 1 until the next edge comes, next positive edge comes. At each positive edge, you look at the data and decide the output, and that output remains until the next clock edge comes. And again, at the next clock edge, look at the data and decide the output. Now, it is not the same as this, but now at least here the output remains stationary for the entire clock period. In between there is no output change. The positive edge triggered, if you apply this, the flip flop, it happens only like this. Changes for one clock period, one clock period, one clock period. A change in the input of the clock, even though it occurred in the middle of the D pulse, middle of the clock, it is recognized here. So that way is different from the behavior of this. So even in positive edge triggered flip flop, you have to be careful not to change if you do not want even though the output will change only now, if you do not want to have this change in the input when the clock is high to affect the output, you should be careful not to give input changes or not to change inputs when the clock is high. Negative edge triggered flip flop, the same logic applies, except that we will now look at the negative edges than positive edges. What is the negative edge? Negative edge is one which goes from 1 to 0. So this is a negative edge. This is a negative edge, negative edge, negative edge, negative edge. Each of the negative edges, you look at the input and decide the output. Here it is 0, the output is 0 for one clock period. At this point it is 1, 1 for the one clock period. At this point it is 1, 1 for one more clock period. At this point it is 1, 1 for one more clock period. This point is 0, 0 for one clock period. This point is 0, 0 for one more clock period. This is 0, 0 for one more clock period. That's all. And curiously, this is same as this. So a master slave flip flop works as a negative so I have a choice now. I can have a master slave flip flop, I can have a positive edge triggered flip flop, or I can have a negative edge triggered flip-flop. The waveforms are given. An identical waveform of the negative edge triggered flip-flop is identical to the slave waveform of a master-slave flip-flop. If you want the waveform of a master-slave flip-flop identical to the positive edge triggered, I can do it by giving the negative of the clock to the master and regular clock to the slave. I now had a clock which I fed to the master, inverted it and fed it to the slave. Instead I take the clock, invert it and give it to the master, and then invert it again and give it to the slave. That means the original clock is going to slave and inverted clock given to the master. Then the behavior will be opposite. So master slave flip-flop will behave like a edge trigger, positive edge trigger flip-flop. So I can have any combination of the outputs, any combination of behavior, any behavior that you want can be achieved. So having talked about latch being a storage element, a bit storage, 1 or a 0, and making sure that we need some timing or a control pulse to decide when the data will be stored, we introduce the clock, and when the clock latch we call it as a flip-flop, and then we had a SR flip-flop, and we wanted a single input, so we made a D flip-flop. Instead we wanted to remove S is equal to R is equal to 1 condition, made it a JK flip-flop, and we worried about racing and removed the racing by introducing master-slave concept or a edge triggered concept, and also had a T flip-flop where only toggling will happen, nothing else. And I also explained to you the behavior in terms of waveforms and everything, circuitry, symbols, characteristic tables, and waveforms. Next question is, what do you do with all these flip-flops? D flip-flop, as I said, is simply used for data storage. So you have a data and you store a bit of information, you give it to D and clock it, it will store it, it's available as the output, and you want to change it, you put another value of D and then clock it again. JK, I said, in addition to data storage, of course data storage of JK will be, you put 2 inputs, 0, 1 for 0 storage, 1, 0 for 1 storage. In addition, you can also use this toggling mode. So first let us look at that feature, because data storage is a simple thing. I put a data, I clock it, it is storage data. SR and JK, I need to do the same thing, except that data has to be 0, 1, 1, 0 combination. So the one which will not be, which is new, a feature which is sort of different, is a toggling feature, and see whether we can use a toggling feature. So let me draw a JK flip-flop. Now hereafter I will only use boxes, blocks. Use a block, it's all inside the circuitry. So let us say it is an edge triggered flip-flop or a master slave flip-flop, it doesn't matter. Let me call it a negative edge triggered flip-flop or a master slave flip-flop. Master slave and negative edge have same behavior, I told you, right? So by the way, when you write the symbol, let us say JK, and put clock here, this assume it is a level triggered clock, level triggered flip-flop. If you think it is an edge triggered, you have to put an arrow like this, a knife edge. It is a point, means that there is only one point in time, at one instant time the output can. This is called edge triggering, symbol for edge triggering. If you put like this, a positive edge triggering. So this is level triggering. You put like this, it is edge triggering, positive edge triggering. And if you put like this, it's an arrow with a bubble. Bubble is always inversion. Wherever you see bubble, that's why in inverter you have a bubble, NAND gate is a bubble, NOR gate is a bubble. So bubble stands for inversion, so it's a negative edge trigger. These are symbols used. I don't have to say every time. Because we don't have a separate symbol for master slave. We put like this master slave also, because master slave behaves like a negative edge triggered flip flop. So let me assume it is a master slave flip flop or a negative edge triggered flip flop. And I put a j is equal to 1, k is equal to 1. When j is 1, k is equal to 1, what happens is output? Output. What does the output do? Toggles. The present output is the complement of the past output. The output during this present clock cycle is the complement of the output during the previous clock cycle, or the output of the next clock cycle is the complement of the output of the present clock cycle. This mode is called toggling mode. I think I told you enough about this. Why can't you say that? Toggle mode, right? So this toggling action, so I am going to draw a waveform, clock waveform. So negative edge triggered or a master slave flip flop, doesn't matter. So I am giving this clock here to this input. I am making j is equal to 1 and k is equal to 1. What is a 1? 1 is a 5 volts or a high level voltage. It could be 5, 3.3, whatever voltage you choose in your technology. Now, let us assume initially Q was 0, and at the negative edge the output will change. It will change to the complement of what it was. So it was 0 to start with. This is time axis. This is 0 to start with. At this point in time, it will become 1 input. Output changes to its complement, and I am giving this clock input and the clock negative edge, because it's a negative edge. Original Q was 0. At this point the Q becomes what? 1. Why do you take so long to say it's 1? Why are you so hesitant? 1. It becomes 1. And at this point it becomes 0. At this point it becomes 1. You don't have to assume that any question will have a trick in it. Also ask simple questions. Now, can you not see something in these two? For every this clock period, the period of a clock is, as I defined earlier, a period of the clock as a point from which you take you start from one point in the waveform and reach an identical point in the next waveform, next cycle. So here to here is the period. From here to here is a period. Here to here is a period. And in this case, this is the period. For every 2 clock periods, here this clock period is 1. So we have 1 period for every 2 clock period of the clock. Or it is positive for one whole clock period. Earlier clock period is half positive, half negative, half 1 and half 0. Now for whole clock period is 1. Next whole period is 0, next whole period is 1, and so forth. So I am having a reduction in the increase in the clock period by a factor of 2, or reduction in the frequency by a factor of 2. So if I want to divide a clock frequency by a factor of 2, I can put it through the JK flip-flop and take the output of the Q. Yes or no? So it's basically a JK flip-flop with J is equal to 1, K is equal to 1, or J is equal to 1, K is equal to 1 is a special name for it. It's called toggle flip-flop. I said that, right? So instead of showing it JK flip-flop, you can say T is equal to 1. When J is equal to 1, K is equal to 1 is called T mode, toggle mode. The toggle flip-flop is a divide by 2 flip-flop. Divide by 2. Now if I take another flip-flop, whose output is again J is 1, K is 1, and this clock period, I am going to not give this clock, I am going to give this clock, a divide by 2 clock. If this clock is F C, F sub C, this should be FC divided by 2. Is that right? The FC by 2 would be fed as the clock to the second flip-flop. So the output would be FC by what? 4. So we'll call this Q1 or Q1, call this Q2. Q2 will remain 0. Here it will go 1, 0. This is my Q2. So every clock pulse period becomes half a period here. So one clock period of this is equal to 2 clock periods of this. Now every clock period becomes half clock period here. And I can go on multiplying, dividing this further and further. So if I have 2 flip-flops, I get the output as FC by 4, divide by 4, count, divide by 4 circuit. So if I have N flip-flops, let us say P flip-flops, P JK flip-flops with J is equal to 1, K is equal to 1, P JK flip-flops with J is equal to 1, K is equal to 1, divides the input clock by 2 power P. 2 power P. So very one thing you can, straight away one use you have got for a flip-flop. I want to divide a frequency divider. I have a large frequency, I want to divide it for many reasons. Why don't you think of this as a thinking assignment or reading assignment, working out assignments? I will have a thinking assignment. Can you think of places where frequency has to be divided? Just, it's a very simple general knowledge question. Just come up with some answers. Where will you need a frequency to be divided? Where? Watches, yes, a good example. Yes. Minutes has to be divided, seconds has to be divided into minutes have to be divided into hours have to be divided into days, and days have to be divided into weeks, and so forth, right? Good example straight away. So one simple use of this flip-flops, at least in the toggle mode, is to keep on dividing the clock, input clock, original clock by a factor of 2 every stage. There are P stages, it gets divided by factor of 2 power P. Now, I don't have space here to draw these waveforms. Supposing I have 4 flip-flops. I'll do it here, maybe. Four JK flip-flops or negative HTK flip-flops. JK, all J is tied to 1, all K is tied to 1, this is Q, 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 Q. I'll call this QD, QB, QC, QA, QB, QC, QD. So this will be JA, KA, KB, JB, JC, KC, JD, QD. So this flip flops A flip flop, D flip flop, C, B, A. The 4 flip flops A, B, C, D, all negative edge triggered JK flip flops. I'm connecting the outputs like this. If you can look at this, when the first clock is, let us look at only the zeros. When the first clock becomes 0, this is 0, the output of this is 0, 0, 0, 0, there are 4 zeros. Then this becomes 1, this continues, okay? When this, after this, this becomes 1, 0, 0, 0. Then this, when 1, this becomes 0. So the Q, the first flip flop, immediately QD flip flop, let us, for every clock period, it goes from 0 to 1, 1 to 0, 0, 1, 0, 1, 0, 1, 0, 1, like that. QD, QC goes 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. Because every 2 clock pulses of the QD will only make this one change. Now this will be again repeated. So this will be remaining 0 for 4 clocks, then become 1 and remain for 4 clock pulses. This will remain for 8 clock pulses 0, another 8 clock pulses 1. So if you want to draw, instead of drawing waveforms, of course, since I don't have space to draw waveforms for 16 clock cycles, I will do it in binary. So supposing this clock is QD, QAB, QC, QB, QC, QD. This is 0, 1, 0, 1, 0, 1, 0, 1, 0. 3, 4, 5, 6, 7. QA, QB, QC, QD. This will be 0, 0, 1, 1. The value of QD during clock period, let us call this clock period, this is clock 0, we will clock 0, 1, we will all start with binary, no? 0, 1, 2, 3. So during clock period 0, all the outputs are 0. During clock period 1, during clock period 2, so during clock period 15, what does it tell you? It tells you I have a circuit to count the number of clock pulses. All I have to do is to how many clock cycles have elapsed from 0. All I have to do is to look at the waveforms of the clock A, B, C, D. If QA is 1, QB is 0, QC is 1, QD is 0, I know it is 1, 0, 1, 0, which is the 10th clock pulse, counting 0 as 1. Starting from 0, it is 10th, actually is 11th clock pulse. But we have to always number from 0 to 15 because there are only 4 bits. So this also can be used as a counter. The divide by 2 circuit, divide by 2 power n circuit can be used as a 2 power n counter. So this is 2 power 4 counter. Using P flip-flops, we can have 2 power P counter. When you say 2 power P counter, it counts from 0 to 2 power P minus 1. 2 power P is 1 to 2 power P, but we also have to start with 0. So looking at the waveforms of the 4 outputs A, B, C, D, we know that it goes from 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, 1. Any combination of outputs you can look at and see this is some 15th clock cycle, this is 13th clock cycle. That means including this, starting from 0, 14th clock cycle, this is the 13th clock cycle if 0 is counted as, if you start the count from 0, start the count from 1. So up to 15, after that what will happen? After 15 it will become 0, 0, 0, 0, so you cannot count beyond 15. With 4 flip-flops I can only have a 2 power 4 counter. If I try to give the 16th clock pulse, what will happen? This will become 0 because this is 0, 1, 0, 1, 0, 1, so this will be 0. 0, 0, 1, 1, 0, 0, 1, 1, so 0, 0, 1, 1, so next will be 0. 4 zeros, 4, 1, 4 zeros, 4, 1, so this will be 0. 8 zeros, 8, 1, so this will be zeros. So 16th clock pulse will revert it back to 0, 0, 0, 0. Again I start counting. So it's called a modulus counter. So modulo counter. Modulo 16 counter. That means after 16 it is 0. Or modulo 2 power n counter. Modulo 2 power p counter. So if you have p flip-flops, I can count any pulse starting from 0 to 2 power p minus 1, and if the next pulse comes 2 power pth pulse comes, all of the flip-flops will become 0, 0, 0, 0, 0. So I will have to start all over again. So we have already seen 2 uses of this flip-flops. One is that it divide this by factor of 2 for clock division, like somebody said in watches you can use it. Other thing is use as a counter. So suppose I want to count the number of people in this room. All I have to do is to put this counter on the door, and every time the clock will be the one will be generated by the person coming. As I said, the clock need not be the same period of duration or same duty cycle. So anytime a person comes in the room, there is a momentary going from 0 to 1 back to 0. That is your clock. And I use this to count into my counter sequence. So at any time I look at the number of the pattern of the counters, the waveforms of the counters, based on the combination of zeros and ones in these counters, I can say how many people have come into this room. So it's a counter. Basically a set of flip-flops could be used as a counter. So binary counter, because we can only count binary values, so you can make it decimal later on. We'll see how to do that. So this is a 2 binary counter. It's a binary. We'll see some other uses of this, and also if you want to terminate now, the problem is I can terminate only when the number is 1, 1, 1, 1. Suppose I want to count up to 10. For example, you would like to count up to 10 and go back to 0 in a decimal counter, right? 9, from 0 to 9. I would like to count from 0 to 9 and back to 0. How do I convert this into a counter which can count from 0 to 9 and back to 0? Or any other arbitrary value. Suppose I want to count up to 12. I want to count a dozen. I want to pack something, dozens. But dozens, I want to keep dozens of, I have a product to be packaged. Every time I want to count 12. How do I do after 12? I have to become 0, 0, 0, 0. Is it possible? So how do we make it count non 2 power n values? And if you want to count up, it's all right. When people leave this room, I want to know how many people have left this room. That also I should know. Counting down also should be possible. So how many people are there in this room will depend on. So as people leave the room, the count has to reduce by 1. So can we convert into an up counter, into a down counter? Can we count into a counter which is converted into a counter which is, you can count non 2 power n values, etc. We will see in the next lecture.